All right. We have 10 people here, one online. Any question? Yes? No? So last time, Tuesday, we started the whole form definition. We had a nice lecture by Jung Ho and discussion by Jung Gi. Today I will start with the second part of whole form definition of my lecture. And then we move on to Lion's class, leaded by Min-Sub and Matteo, right? And there was some schedule changes, more changes, because the guest lecturer want to have their lecture toward the end of class, so the changes done. Then the other classes are moved a little bit upward. The second one also changed. That your schedule moving 1 week or half week earlier. Okay, and we move on to whole form definition second part. This one. Right, whole form block options. There's a question last time. Block options is here. Is the definition. That LBT multiplied by LBT, it is volume, right? Volume of a box. Box of length of size of length and B and T. T is depth, not depth. Depth. The submerged portion of outer box. My body. What can be the block options of my body? I should make a convexer, right? Bounding box, right? And then my body volume divided by bounding box. That is the CB. But it is only underwater, not whole ship. So underwater, only underwater. So it shows you how full is the ship compared to the box. Barge is a type of ship. Barge is a box-shaped ship. Barge. We can see somewhere near river or near coastal area where there is some sand moving, or land-based crane is up on the barge. They are using for construction somewhere near the river or ocean. Barge used, and that is just a box of steel plate, simple. So, but it is not easy to moving them in the water. That's why we should have a slender body, move fast. So block option of the barge is almost 1. This kind of ship is say 0.7, something like that. So Navy ship is very small, 0.5, something like that. Block option, because they need to have a faster running for the better. But cargo ship usually have a full, they are saying fullness of the underwater. V is a volume, not speed. Oh, there is a video.
I don't think so, Marcy.
I don't think so. 나는 그렇게 생각하지 않는다 라는 말이죠.
Types of hulls. Flat-bottom boat. They are generally less expensive to build and have a shallow draft. They can get on plane easily, but unless the water surface is perfectly calm, the ride can be rough because the flat bottom hits each wave. They are less stable and require careful balancing of the cargo and crew. V-bottom boat. The V-bottom rough waters, but needs more power to achieve the same speed. Many runabouts use the V-bottom design. Round-bottom boat. It moves easily through the water, especially at slow speeds, but tends to roll unless fitted with a deep keel or stabilizers. Many trawlers, canoes, and sailboats have round bottoms. Multi-hull boat. Catamarans, trimarans, pontoon boats, and some houseboats have a multi-hull design. The wide stance gives greater stability. Each of the hulls may have any of the bottom designs described above.
Right. Type of hull and CV. Okay. So CV value is 1.0 for a rectangular pontoon or barge. Here, you see the barge here. This one. The ship here is almost box shape. So it is good for carrying more cargo. Good for carrying more cargo, but bad for speed, running. So it is used for slow speed, short distance transport. So you see that this is a near river side. Short distance travel. Big curve. And this one is just a playboat, but this one looks like a slender, or looks like oceanographic research vessel. Great Lake bulk carrier or barge here, barge. You know where is the Great Lakes? Great Lakes. Yes. Great Lakes. Great Lakes. USA. USA. Yes. Yes. No. No. All right. Great Lakes, big lake. Big lake. I myself has between Canada and US. Between Canada. Myself, I studied in United States for my PhD in University of Michigan. Michigan is the name of one of the Great Lakes, Michigan Lake. So there are 5 big lakes together, connected together. Between in the middle of the United States, and then between Canada and so north, middle, or even east side. Detroit. Have you heard of a city named Detroit? Yes. Detroit. Yes. No. Detroit. Detroit is one of the big cities in Michigan. Right. Detroit is famous for the baseball team, basketball team, football team, American football team. Right. Also, industrial wise, the automotive industry center of United States is Detroit. Big automaker, GM, Ford, you know GM Ford, right? And how about Chrysler? Chrysler, right? About 30 years ago, those 3 companies were the world top 3 automaker until 30 years ago. Now it is not, right? GM is not number one. GM must be number three, something, right? But anyway, until 30 years ago, from the beginning of automotive industry, started 100 years ago, Big Three, GM, Ford, Chrysler was located in the same city of Detroit. So Detroit is, I'm saying because these Great Lakes has the reason for Detroit to be the center of automotive industry. Transportation sense. Anyway, for such like this ship is used for the Great Lakes. High CV, low speed, high cargo capacity, low CV, low resistance, speed, resistance, and good sea keeping. Sea keeping is there's a typhoon is coming, ship is jumping on the wave, right? But it should be safe. Right? That we call seaworthiness or sea keeping. Rough wave, rough sea, ship is okay. Right? Otherwise, this kind of ship flips. Right? Because of the big wave. Mid-ship section coefficients, we call it CM. Yeah. CM is area in the middle, and B multiplied by T, B multiplied by T, T is draft, but small d can be used, or many times T, draft. Because uppercase D is a depth, lowercase d is a draft. It's confusing, so that many people use T instead of small draft, lowercase d. But it is can be used. Anyway, rectangle, B multiplied T, this is rectangle, and then area of the shadow area. So remaining part is only small, right? Here. So this coefficient is very high usually. But for me, for myself, what can be CM for me? So I should have a rectangle around my body, middle part of my body, and then cutting area, sectional area. It is not so high like this. It can be 0.8, depending on the shape. Maximum section coefficient. It is very similar to big ships, mid-ship or maximum area. For my body, probably is around here is CM, not here. CM is in the middle length. CX is maximum area, somewhere over here. Okay? So it's different. For the ship, big ship usually same. CM and CX is same, but small ships, fishing boat, yacht, they have a little bit difference between location and DX versus. Okay. So this mark is here. But this is a badge for the Society of Naval Architects and Marine Engineers of the United States. Badge. So they use this mark as their badge. Longitudinal prismatic coefficient. Again, the volume. But here it is not LBT. Here is L multiplied by AX. We just know that AX is a maximum area. Right? AX. So,
what is the physical interpretation of this question? Why we define this?
see, we want to know how the ship is full or slender. To evaluate the weight, performance, resistance. As a designer, I am comparing. I'm trying to design a fishing boat. I'm trying to design a bulk carrier. I'm trying to design a battleship. What can be the good CV for this ship. I should decide how slender it should be, how full it should be. So we are trying to design it based on the purpose of this. And then coefficients are used for that purpose. Prismatic coefficient. So this is also another division, but not a box. It is extension of this area, maximum area, into the L, and then volume is same. We call this as prismatic coefficient. So here is the summary: center of volume, center of buoyancy, vertical center of buoyancy, longitudinal center of buoyancy, midship mark. This is a midship mark, and longitudinal center of flotation area, where without change. Similar one, but a little bit different. Similar. Center of buoyancy. Center of buoyancy can be. I forgot to bring my center of this coffee. Center of this coffee. How can you calculate this one? Center around somewhere here, but in the center. Right? How about center of my body? Volume or weight? A little bit different. Volume is center of my body volume, and center of weight volume. No, volume. Center of gravity, CG, should be similar but a little bit different, right? And center of buoyancy is for the flotation volume. The buoyancy is supporting from the water. And this one is 3-dimensional point, XYG, right? And vertical center is a G value of this one. L value, X value of the center of buoyancy. Okay, and this mark and flotation. This is area, not volume. This one. So this is a volume, underwater volume, right? Underwater volume. This one is underwater volume. Right? Underwater volume. So buoyancy should be center of buoyancy should be center of volume of this underwater body of the ship. Center of volume. Center what was the name? Center of flotation, something. It is center of this area. Not volume. Center of this area. This is center of flotation. That's here. Center of flotation. Area, not volume. This one is a volume. Center of volume. Okay. And this one, and then so center of flotation is here. We call this is a water plane area. So center of water plane area is center of flotation. So water plane coefficient is area divided by area. But this area is L multiplied by B. CWP. And underwater hull form? Same one. Right. So now why we are talking about complicated coefficients again. Here is the sum and sum, not all of them. Root number. Root is a famous person, right? He developed a number. This is a non-dimensional speed size ratio. So ship, battleship, fishboat, razor boat, bulk carrier, oil tanker, container ship, cruise ship. Which ship is faster? Probably Navy ship, battleship should be fast. how can you calculate? How can you make the speed, high speed of each ship as a number? So that he developed this word number. Speed size ratio. Because big fish and small fish running together. Big fish, small fish, swimming, racing. Big fish is more easy to win. That's why we are saying size is important. Speed, not only speed. Small fish, they looks very fast, but it is not fast with that. It determines speed and power characteristic. So we need to know what engine should be used for my design. So first number is GL, so L and V is the most important numbers. Now the gravity constant is used for non-dimensionalization only. So for the designer, V and L is. So 500 naval vessel moving at 10 knots, that what is something kilometer something. Knot, root number is low. 150, this small ship. Same speed, but root number is high. Because this length, speed is same. So big ship is easy to have a higher speed. That's why we are using speed length ratio without G, right? It was used for a long time in traditional, before Frege. He found that this one has a dimension, but it is not good. So he tried to make a non-dimensional option. New option is developed. Right, and then it comes with a displacement length ratio, not speed length ratio. It's displacement length, the size and length ratio. Fatness, slimness, and predicting speed and power. So displacement length ratio is defined by, this is a volume, total volume, underwater volume, and length cubed. So it is very similar to block option. See, volume same, but LBT or is a LLL, right? So similar to block option. So we call this. Now it comes with displacement ultralight and heavy, ultra heavy. The displacement length ratio is increasing like this one. Here is an oceanographic research vessel, power yacht, great bulk carrier. The block option is in range, speed length ratio, and displacement length ratio. Example. So as a designer, you should decide what coefficient for your ship. Right? How do you calculate these numbers? This is very tedious work, especially in early days before computer era. So when I was a student 30 years ago, I do my calculation this one without computer. Very long time taking and also error, too much errors. Right? Now you are very lucky. Just button, then coefficient is coming, right? Very easy. So you should know how they calculate. So area integration, right? Integration area, this area. Integration in scope. Easy. But how do you do that yourself? By pen. It's not easy, huh? You know how, what is the meaning, but by pencil, it's not easy. So Bonjian is a personal name. It's a sectional area code. Each section of the ship at this point, the cutting a fish or myself, cutting each section, we have a different sectional shade and area. Right? This is a sectional area curve. And this one together converted into this. Each section area is plotted here. And then integration of this total area, what can be this area? Can you answer? What is the meaning of this area of curve? Once again, sectional area at this point, that one is drawn as a coordinate here. Sectional area, this vertical sectional area. And then integration of the
volume of the sheet.
right, volume of the sheet. This area should be volume of the sheet. In old days, when I was a student, I do it myself in this way to calculate the volume. Volume is important. Also, where is a longitudinal center of volume? Vertical center of volume. Calculated by this is LCV, longitudinal center of buoyancy. This is volume. They somehow they find out by somehow. So again, CP, CM, and then CP is CB divided by CM somehow. The same definition is already done. So I do myself to draw this one to calculate the volume. It is not easy. It takes long time and also error prone, right? For you guys, you can use computer softwares to do request and correct. Longitudinal center of buoyancy and longitudinal center of flotation. This is the equilibrium of displacement between forebody and afterbody. So for me, my body, where is the center of buoyancy? Is it up part of my middle body or lower part of the center of buoyancy? Forebody. This is important for wave making resistance, wave pattern, and breaking resistance and CT. The wave is coming, ship is running, it is hitting the wave, right? So ship is rolling, pitching like this one. So forward is important for wave fronting. Afterbody important for resistance, propulsion, wake distribution, cavitation, engine arrangement, front part of the ship, and end part of the ship, afterbody of the ship. And here you see the LCF, longitudinal center of flotation, is moving down in this way because this is the area center. Here is a block option and optimum LCV. Right. So when as a designer, I choose that my ship should be CB is 0.88, 85 or something, 86, 86. Then optimum LCV should be around somewhere here. So I'm using this curve to find out the proper numbers at the beginning. Oh. Oh, this final slide. Good.
많이 설레요. 설레고 많은 사람들이 우리 단체를 좀 더
Right. As an example, take water lines. If you were to take the water line plane, make a bunch of different copies of it, and run it from the key.
See that Naval Engineers Education Center. This is for Navy. Naval Engineers. Navy Engineers Education Center. Short course.
Hello, my name is Laura Alford. This is the first lecture in our series on hydrostatics, and it is on the geometry of ships. So ships, like all specialized things, they have their own set of terminology that might be unfamiliar to you if you have not run into it before. So that's what this lecture is sort of aimed at familiarizing you with. So the first thing and the major thing is the hull. The hull is the big outside part of the ship that you see if you go see a ship down at a dock. The front part is called the bow, and the back part is called the stern. Left is port, and right is starboard. If you are standing in the middle of the hull and you're walking towards the bow, you're said to be going forward. And if you are in the middle of the ship and you are heading back towards the stern, you're said to be walking aft. Now you can see from this is just an example hull here, and this little kind of there's a bulbous bow. That's that little part that sticks out. This is very complicated, right? It's very curvy, it's higher in some parts than others, it's narrower in some parts than others. This is pretty complicated. And it gets kind of tricky talking about the hull if you've got a problem and you're trying to explain to somebody where exactly it is or what's going on. So we've got some reference planes that we can use to help ourselves with. So there's a big vertical one that goes down the center line of the ship. It is very creatively called the centerline plane. There's a horizontal plane called the waterline plane and a transverse plane that's called the midship plane. You'll notice this little symbol here with the circle with the two arcs bisecting it, sort of. That's the symbol for the midship. That's the middle of the ship. So if you see that symbol, we'll run into that before, but that's all it means. It's just put at the center of the ship. Right. As an example, take water lines. If you were to take the waterline plane, make a bunch of different copies of it, and run it from the keel line, which is the bottom of the hull here, all the way up to the top deck, you get these blue lines here. And from the side and from the front, they look straight, right? Because they are horizontal slices of the hull. But if you look at this from the top or from the side, sort of from this oblique view, then you get a sense for the curvature of the ship as it changes from the keel all the way up to the top decks. And so now we say, okay, here's some lines. We can start to see more of how the hull is changing, what its real shape is here. Similarly, if you take the midship section plane and you take a bunch of copies of it and put a bunch forward and a bunch aft, you get what are called stations. The stations here from the side and from the top look straight, which is good. That's what you want. And then from the front or the back or from this oblique view, now you get these sectional curves here. And you can see that they illustrate how the hull is changing as you go from the bow to the stern. Here, you see down below here, right, if you were to plot all those red lines on top of each other, it would get kind of busy, it'd be tough to see which ones are going where. So generally we put the stations that are forward of midships on the right hand side and stations that are aft of midships on the left hand side. This way you can see how things are changing easier. And most ships, almost all of them, have a port starboard symmetry. So you're still retaining all of the information here. So finally, if you take the centerline plane and you take a bunch of copies and you send them port and starboard, you get what are called buttock lines. So again, from the top and from the front or back view, you get straight lines. But then if you look at it from the side or from this oblique view, now you start to get these contours as you go from port to starboard or left to right. So now you can see how is the ship's hull changing from side to side. And you can look at these lines, and they're sort of like the lines of pressure on a weather map, right? The closer the lines are on a weather map, then the higher the wind is going to be. Similarly, the closer the lines are on these slices here, the closer the lines are, the more curvature there is, and the farther apart they are, the less curvature there is. The design waterline is going to be the station area, and it's shown in red here. So again, it's not going to be the total area of the hull, it's just what corresponds to being underneath the water. Similarly, if you do this at midships, then you get the midship station area. And the same thing, it's just the area below the design waterline at midships. Now, if you do that all along for all of your stations, you can plot the sectional areas on the sectional area curve, and you can see that it has less area at the bow, and then it increases as you get towards midships, and then it comes back down, and you have less area at the stern. Because the area would then be related to the volume, this kind of gives you an idea of where your buoyancy is going to be coming from, which we'll talk about later. So the bulk of buoyancy is going to be coming around midships, not so much at bow and stern. Your hydrostatics program will calculate this for you. You can do it for a lot of different drafts because there'll be a bunch of different drafts that you need to be concerned with. Then you mark one as the design waterline. You do some that are greater to what I've got here. A note that the block coefficient is actually equal to the prismatic coefficient times the midship section coefficient. So if you know any two of those, you can calculate the third. All right, so some notes to remember. All of this stuff that we've talked about here will change with draft. So going back to that sectional area curve where you calculate it for different drafts, you do the same thing for all of this stuff. The pictures that are shown here are just instructional. Your ship will look differently. And the dimensions listed here are the molded dimensions. It means like from the very outside of the ship to the other very outside of the ship. They don't include the plate thickness from when you're actually building the ship. So it's just things are changing.
Why the station shape or curves are important? Because we need to build the ship using steel plates. So you need to put steel plates one by one here, one by one here, one by one here. But this one is more complicated area. Steel plate. So cutting and bending and welding to make, so trying to imagine that you use just a cardboard as a steel plate to make a small size ship by putting cardboard together, stitching together. But in the shipyard, this is a very main work of a thick plate, say something like a 2 centimeters thick, big steel plate coming from steel company, cutting, bending, welding to make this. But your design, all these curves, this is most important for them to cut, where to cut, how to bend, how to weld without any error. Right? Precision. Question. No question, then we stop here. Right? So we can move on to Minseok.